Bruno Bauwens.
Thank you. Hello, thank you for coming. I will talk about two randomness, and I will give some simple proofs about results I find nice. So I'm going to talk this in three parts. While giving the simple proofs, I found some improvements to the statements. So I will discuss this first, and then I will discuss the plain characterization and the prefix-free characterization of two randomness.
Sorry.
Oh, sorry, I forgot, yeah. Sorry.
Do we have to start again then? Or?
Yeah. So now I'm in the mic.
Yeah.
Yeah. So I will talk about two randomness. I just repeat for the video. I will talk about two randomness, I made some simple proofs about plain and prefix-free characterization, and while making these proofs, I found some stronger statements which I believe are also interesting. So I will discuss in the first section, and in the second and third section, I will talk about the non-trivial directions of a prefix and plain characterization of two randomness. Okay, so the general picture, Solomonov and Kolmogorov defined Kolmogorov complexities in the mid-60s, and then at the same time about Martin Löw also defined a notion for randomness of infinite sequences, and then was the question, how are these two related? And then in the 70s, mid-70s, people defined a prefix-free variant of Kolmogorov complexity, and then there was a theorem which I reformulated slightly different, but you will see why, that says that if a string has initial segments that are not too much compressible, then its infinite sequence is random according random in the Martin Löw definition. Okay, and then many years later, so 30 years later, there were other connections between randomness and Kolmogorov complexity. So the Nies-Steffen-Terwijn-Miller theorem says that the sequence is too random if infinitely often plain complexity is maximal. And then a few years later, the same result for prefix-free complexity was discovered. So n plus k of n is the maximal value for prefix-free complexity of a string of length n. So the second one also states that a sequence is too random if prefix-free complexity is maximal. Probably everybody knows this in the audience. Then there are some easier directions. So Solovey showed that plain deficiency is always bounded by prefix-free deficiency. So this implies the 1 to 2. So if prefix-free deficiency is small, we directly have plain deficiency as small, so the lim-infs are also small. And then from 2 to 3 is also not so hard to show. The big problem is to go from 2 to 1 or from 3 to 1. So to go for 2 to 1, we should like to have the statement with the other inequality, but this is false, as Solovey showed. So the one remaining, if we can prove 3 to 1, then we're done. And I will present at the end of the talk a small proof for going from 3 to 1. Okay, but as I told you, I found some stronger version of the theorems. So here are the three theorems, and we can quantify these theorems. Like here we got a nice O1 constant, and we want to relate it to something else. And this was done by Getch and Levin. I think Getch and Levin defined the randomness deficiency for infinite sequences. So for this we need first to define a lower semi-computable function, and we already saw some definitions of that in the conference. I pick just the one I will use. It's a sum of uniformly computable basic functions. So these are functions that only depend on an initial segment of omega. So we just enumerate such a function. And then such a lower semi-computable function with finite integral is an integral test. And there is a maximal integral test up to O1 factor. And the logarithm of this maximal integral test is the randomness deficiency. And then there is a nice property. Randomness deficiency is infinite if omega is non-random, and vice versa.
It only depends on the first bits.
So each function fi depends on, for example, first I bits of omega. Yeah. So that's the equivalent with other definitions. If you choose fi of omega simple enough, I'm not quite sure whether you need the amount of bits you use of omega must be computably bounded or something. I'm not so sure about that, but anyway, I assume that. Okay, so the quantified versions, omega is random. If this holds, this becomes that the randomness deficiency equals supremum of deficiency. Oh, I switched these two. No, sorry, it's right. I switch it here. Then the Nice-Stephan-Terwijn-Miller theorem has the same for randomness deficiency relative to 0 prime. That was shown by Miller's proof. He formulated a little bit different, but it's not so difficult to get this form. And then there was, for the remaining characterization, it was not known whether there is a connection with randomness deficiency, and I don't think with this proof you can have it easily. So you need to strongly rearrange their proof to get the quantified statement. Okay. So I showed that that randomness deficiency relative to the halting problem also equals this. So that completes a nice picture, because if you take rather than lim inf, lim sup, then things are either diverge or constant. If you use sup here or inf, any other combination diverges or is trivial, and all the other combinations are equal to each other. There is a thing with monotone complexity, then there are logarithmic precision, but it's not clear whether you can improve to constant precision. Okay, so now I will use 10 minutes for each proof that follows. So for the plane characterization, here is a non-trivial direction.
I'm just surprised that you have the lim inf and not simply inf.
If you use inf and then you take a sequence of length 0, so if you put n equals 0, then you have a constant. Yeah, so indeed, yeah, a constant. So we must use lim inf. Okay, Conidis, we will use an even more general statement, and that's Conidis theorem. So first, let's see what's the problem with this. For every n, we can assign a set where the first n bits are compressible. So for n0, n1, and so. And the problem is we got an infinite series of sets. And then we want to find some tail, if there is some tail in every set. Then we want to put all these tails in a set of small measure. So if randomness deficiency is big, then there is just little red in every set. So we can associate the lim_inf. Oh, I forgot the lim_inf here. Yeah, sorry. That's so when we want to show that lim_inf is high, then we need to show that if lim_inf is high, then we can get all this corresponding omega sequence in a set of small measure. And this happens by Conidi's theorem. So we say that some element is a tail member, so this represents Cantor space, and the red corresponds to a family of sets. So Conidi's theorem is about a family of sets, and if there is a member in the tail, then we can make a set for all these tails that has small measure, on the condition that every set has small measure. So classically that's an easy result. If you got an infinite family of measures and they all have measure at most epsilon, then the lim_inf of this set also has measure epsilon. But if you want to compute the lim_inf, you need halting problem relative to the halting problem. One halting problem to decide whether an element is in the set, and the second one to decide if they are in all future sets. But we can do it with one halting problem. That is the easy thing. So without making the set too much bigger. And to explain this, I first go to the discrete case. And this discrete version of Conidi's theorem has another very nice result due to Nikolai Vereshchagin that relates complexity relative to the halting problem to complexity relative to large numbers. Okay, what says the lemma? If we got some infinite tail, if every set has at most m elements, then we can enumerate m tails that we can enumerate m elements such that all tails correspond to an element. And that's the theorem. And how do we do this? And we can do this uniformly, having a program that enumerates all the red area if we know m, and if we have the halting problem, then we can just enumerate the cover. So how do we do that? We just okay. The red areas are enumerated, so each time we enumerate the red area, we try if we can put that element also in every set at the right of the enumerated red area. So we try to put it in. And then we see whether for some set, adding this set makes it bigger than m, strictly bigger than m. So for example, here, if we put that element also in here, then there will be 5 elements while we chose m equal to 4. So in that case, we cannot add the tail and we forget about this element and this tail. So we go to an x2 element that's enumerated as the red. And then we try again to add this element everywhere after it. If that works, if that's possible, without increasing one of the sets larger than m, then we do it effectively, and then we have found the first element of our cover. So and we can do that again, check whether there are at most 4 elements in every set, and if this is the case, then we effectively enumerate it. But what happens if our tail is a tail that's really in all the sets? So if all these elements were already in this set, then adding the tail everywhere does not change anything. So if all sets before adding the tail had at most m elements, trivially afterwards they still have at most m elements. So in this case we guarantee that our enumerated tails contains the element in this set. Now this procedure is computable with a halting problem. Why is this? Checking whether a set is too big just happens by a search. We enumerate all sets, and if at some point the set gets too big, then we found the answer. It's not possible. So we can ask the halting problem, will you ever find such a set? And it answers directly. So each time we enumerate the red place, we directly know whether the set is in it or not. Okay, now we got the simple proof. I hope I explained it a bit nicely. We will rearrange it a bit. So I will give the same proof, but such as already in a shape that we can use it to show Conidi's theorem. And we do it as follows. So rather than looking to individual sets, we now take intersections. So we will enumerate the cover as a union of intersections, and each intersection is written as UKL, and you can see here such an intersection. So here is red, red. So the intersection of the first three elements is this bar, and then we add to the orange area the intersection, for example, of the four next sets. So here he is written the intersection of these two blocks. I draw. Okay. So we need to construct K1, K2, and K3, and so on, such that our cover does not contain too many elements. Obviously, if an element is in some tail, like here, then it will be in all blocks for the blocks being large enough. So that's guaranteed. We just need to construct K1, K2, and so on, such that our series of intersection does not contain too many elements and not too big, so we can compute with halting problem. So what we do is try to add the intersection to all sets at the right. Then it might work or it might not work. If it works, then we fix our K1 and then we go to the next K2. So we first guess K1. If it works, then we go to K2. If it's not working, then there must be some set with at least m plus 1 elements. So that means if we also intersect, so the orange area plus the red area must be at least m plus 1. That means there is some place where there is orange and not red, because red is at most m. So if we also intersect with this set, if we increase the intersection, then the orange area decreases at least by 1. So so each time we see there is a constraint violated, we increase the intersection, and then the orange area decreases at least by 1. So that means after a finite amount of steps, we are done by increasing the orange area. And then we found our K1, and then we can start to construct our K2. So we add our intersection to all sets at the right, and then we guess K2. For example, we guess K2 equals 2. And then we again want to add this intersection to all sets at the right. Now, if this is not working, for example here we have 5 places that are either red or orange, then again we take intersection. Before we had at most 4 red places. Now we have 5 places that are red and orange, so 1 place is orange but not red. So, yeah, 1 place is not red. So if we increase the intersection, then then the orange region decreases in size, so again it converges, and so we can continue. And in this way we have constructed our sequence here, such that there are never more than m elements, and it contains all tails, and it is computable with 0 prime. Okay, if we want to prove Conidi's theorem, we don't need to change very much. The problem is we need to soften our requirements slightly. That's the only thing that changes. So we will fix a computable sequence between epsilon and epsilon prime. So epsilon prime will be the upper bound for our cover. First we guess a k1, and then we check whether for every set red plus orange is at most epsilon 1. If this isn't the case, then we add it. If this is not the case, then there is some set where it's violated. So that means there is some area that's orange but not red, and the size must be epsilon 1 minus epsilon. Because red has at most size epsilon, and our requirement epsilon 1, and epsilon 1 is strictly bigger than epsilon. So if we increase the intersection, then we decrease our size by epsilon 1 minus epsilon. So this can happen at most finitely many times. So after some finite amount of times, we found k1, and then we can start constructing k2. And so on. So here there is a violation, we increase the intersection, and then we add it to the set, and so on. So now we have shown Conidi's theorem, and this implies the two randomness thing. So the Conidi's proof was invented by Conidis, but then it was simplified by Collia, by Laurent, then by me, and by Sasha. So it is a long change of simplifications. Okay, now I will quickly say the proof for the Miller's theorem. And here there is some new concept involved. So Miller says if this tends to infinity, then omega is not too random. So that's the negation of the statement. So we have introduce some definition. We say A tails for two sequences A and B that converge. We say A tails are bounded by B tails if there exists some C, such that for all n, the tails starting at n are smaller than C times the tails starting by B. So the reverse is A tails are not bounded by B tails if this ratio is unbounded. And then we got some simple examples. For example, for a universal semi-measure, and if M is universal, A computable, then A tails are bounded by M tails. Why? Because for the individual instances, we have A is smaller than M. And also the reverse. For a universal semi-measure, we can find a computable measure such that A tails are bigger than M tails. And why is this? If we get a universal semi-measure, we can approximate them by initially guessing the quantity of the universal semi-measure, but it will be too low for some elements, so we can delay this access to a later moment. And this, so bounded tails is a replacement for Solovay reductions in Miller's proof. But it's easier to work with bounded tails than with Solovay reductions. So then there is the main lemma. So we work with an integral test, and we can write this as a sum of basic functions. And if the basic functions are always bigger, if for some fixed omega the basic functions have bigger tails then any computable series, then omega is not too random. Very stupid, I forgot to check the converse, but probably it's also true. So that's another way to characterize a two randomness. So how does this implies this? I will not go through the details, but it's just by taking a universal integral test. And now how do we prove the lemma? And this is, I like really much this proof, but of course. So that was extracted from Miller's proof. We need to construct, for every epsilon, we need to construct a set S of size at most epsilon that contains all omega for which the Fi omega tails are not bounded by, rather than every computable function, we use one computable function which we will construct. And if we can show this, then this implies the theorem. So how do we get the set? It's as follows. So if we got an integral test, we can just enumerate it by the sum, and just let for fun imagine that they drop from top to below. So here is F1, and then we enumerate F2 and F3. So here we got F1 plus F2, F3. So we build F. Now that's a bit too simple. So we will let them drop, but in such a way that there are also holes. So we will do Cassera-Slaman theorem in 2 dimensions. And that's what this is actually doing. So we drop F1, and then we will increase, so we get our blocks for a building, but then we increase the floor. So if we see that the area of buildings above the floor is more than epsilon, we increase the floor until it's again smaller than epsilon. So we got a new floor, and then we drop the next stuff. But now he falls on the new floor. We do not need to increase this time our threshold or the floor, because it's still less than epsilon. And the second time we enumerate it, then it's increasing in T3 star. But now we need to increase the floor again, and so we can continue. And if we do that infinitely long, then we get such a thing, a strange building. So we get our original integral test with gaps in it. And then there's a question: does the floor converge to some place? And the answer is yes, because the great area was generated by integral tests, so it's only a finite amount of substance that drops down. And each time we increase the floor, we use in some sense an epsilon fraction of the total weight. So we need to use a constant ratio of our substance that went down. So at some point this T sequence must converge. So what will be our set S epsilon? It will be the set where the buildings exceed level T. So where the gray area is strictly above level T. Now this set has size at most epsilon. How can we see this? Because each time there are more buildings than epsilon, we increase the floor. So if at some stage there was more buildings than epsilon, then at the next stage we would increase it, so we would have a level Tn above big T, which is impossible. Then we can also remark that T is computable with the halting problem, and the places where gray is above level T is just enumerable even without the halting problem. So our set S epsilon is enumerable with the halting problem. And then the last thing we need to say, that if f converges slowly, if the tails of f for some omega are bigger than any computable function, then at some place our buildings are above the ground, above level t. Why is this? Here we sum up just the tail, so we drop the substance, so we get just a sum of the tails of f, and we compare it to the levels of the floor, but this is just a computable sequence. So this distance is the sum of this tail, and this distance is the sum of this tail. So if we look to the ratio, we know it's unbounded, because for our omega we said it must have bigger tails than any computable function. So we know we are above the floor. So that omega is in our set. And so we have covered all omega that satisfies this condition with a set of size epsilon. So this finished the proofs of this lemma. And this finished also my talk. So there is still an open problem which I did not found yet. I thank you for attention, and my paper is on my website.
Questions?
It is really simpler than the original proof, or original proofs.
Okay, for the Miller's proof of the prefix free, it's that involves a lot of computability theory. So Solovay reduction, Kucera-Slaman, Miller-Getch.
We are more direct, even if it looks a little bit more involved.
And the nice thing, we got the quantified version out of this. But we need to...
Quantitative version.
Quantitative version, yeah. But we need to do it in more dimensions, and a special trick is needed, but it actually shows a quantitative version too. And for the plain version, the O1 type version of Miller is completely impossible to read, in my opinion, or for me impossible to read. And the other version is nicer, but I only get logarithmic precision for the quantitative version. And it also uses low basis theorem and things from computability theory.
What's simpler is sometimes subjective. It depends which area you're from.
Yeah.
The proof of Miller using this shading random or n plus k of n that uses that low for omega equals weakly low for k. So if you like that, for instance, then
of course, if you're working already 5 years with low for k sets, then I can imagine the other proof of Miller is
actually weakly low for k, which is, is a much weaker property.
Yeah.
Simpler or not, it's nice to have a proof for the different direction.
Yeah.
It's up to the listener what's simpler.
Yeah.
Other questions? Thank you very much.